I'm a big Lord of the Rings fan, and I remember in Lord of the Rings that Frodo and friends were looking for the one ring to rule them all. Well, Gibbs free energy is the thermodynamic value that rules them all. Gibbs free energy is defined as the maximum amount of energy released from a system that is available to do work on the surroundings. In previous lectures, I talked about entropy and enthalpy and the signs that were favorable for spontaneity. Well, Gibbs free energy is an absolute. If Gibbs free energy is less than zero, a reaction will be spontaneous. It will occur without outside intervention. It is thermally favored, thermodynamically favored. So we can calculate Gibbs free energy by taking the enthalpy, and we recall that the enthalpy is the heat gained or lost in a reaction um, from the system to the surroundings. If enthalpy is negative, it's exothermic. If it's positive, it's endothermic. And then we take into account the temperature in Kelvin and the entropy of the system. Entropy is the degree of disorder, and if it is a positive number, then if delta G is a positive number, then it is thermodynamically unfavored and will not occur without outside intervention. Under standard conditions, remember standard conditions is the way you find it in nature, 1 atmosphere, 25 degrees C, and 1 molar. The equation looks like this. A lot of times you will not be given a temperature, just the aught sign, and you are to remember that that means it's 25 degrees C or 298 K. So here is a typical problem. We have this system, these two reactants forming this product, and they tell us it's carried out at standard conditions. They give us some thermodynamic data, and they ask us to calculate delta H, delta S, and delta G. So we recall that the state function, all of these can be calculated using the sum of the products minus the sum of the reactants. All of these are for 1 mole. We notice that we have some of these species that are 2 moles, so we will take that into account. Let's look at delta H of this reaction. First, I take the products 2 times its value, negative 396, and then I will subtract 2 times the value for SO2 minus 297. I recall that the enthalpy value for all elements is 0, and I see that my delta H is negative 198 kilojoules. Delta S is also the products minus the reactants. 2 things to note. First, these are in joules, not kilojoules. In order to use this reaction, we must make our values match. I'm in favor of taking my delta S value, changing to kilojoules per K per mole by dividing the end result by 1,000. The other thing to note is the entropy of all of these species is a positive value. The only time a entropy value is 0 is for a perfect crystal at absolute 0. There are no negative entropy values. So I will take 2 times the SO3 value and subtract that from the SO2 value multiplied by 2 plus the value for O2, which is 205, and that is 187, negative 187 joules per mole per degree Kelvin. Right now, I'm going to divide that by 1,000, so that becomes kilojoules. So delta G can be calculated by taking delta H value minus 198 and subtracting the quantity of the temperature times the delta S value, and that gives me a negative 142 kilojoules per mole is my answer. That means under these conditions, this reaction will occur spontaneously without any outside help. So delta G rules above delta S or delta H. So if delta G is negative, the reaction is spontaneous in the forward direction, non-spontaneous in the reverse. If delta G is 0, then the reaction is at equilibrium. Remember that equilibrium means that the rate of the forward reaction is equal to the rate of the reverse reaction. So I guess you could think about it as being spontaneous in both directions. If delta G is positive, it is not spontaneous in the forward direction, but is spontaneous in the reverse direction. Let's look at this graph. We're plotting Gibbs free energy on the y and the progress of reaction on the x. And then we're going to look at the slope of the line as time goes on. The slope of this line is negative. That would be our delta G value being less than 0. And so that would be spontaneous when the slope of this line is 0. That is at equilibrium. The slope of this line is positive. Delta G is positive, non-spontaneous. Okay, so delta G is a state function like delta H and delta S. That means you can calculate delta G by taking the sum of the thermodynamic values of the products minus the sum of the thermodynamic values of the reactants. Like delta H, the value for an element, the delta G value for an element is 0. So we can calculate this easily. So the delta G for this reaction would be 2 times the value of the product, H2O2, minus 2 times the water, plus 0 because the oxygen is 0. And that is negative 54.4 minus a negative 113.4. That value is 59 kilocalories per mole. This is a non-spontaneous process, which is good because we would not want our water turning into hydrogen peroxide. It also means that you can calculate delta G as you calculated delta H using Hess's law. Any state function works that way. So we have these two elementary reactions. Here is our target reaction. We are going to manipulate the reactions until they, when spectators are crossed out, add up to our target. So I look at this first elementary reaction, think I want this to go as it's written because I want a diamond to be in the reactant side. So I am just going to leave it as it is. However, the second elementary reaction I want to flip because I want the graphite to be a product as it is in my target reaction. So I go ahead and flip that. And then I flip my value of delta G. Now I'm ready to add everything together. Before I add everything together, I'm going to cross out spectators, things that are exactly the same on both sides of the reaction. And when I add that together, I get my target reaction telling me that I've done this correctly. And when I add these together, I see that my value is negative 3 kilojoules per mole. That is a spontaneous reaction, which means that diamonds turn into pencil lead. Nobody said how fast that occurs, though. Okay, you are going to be asked to estimate the value of delta G given qualitative results of delta H and delta S. You know that delta H is generally spontaneous when it's a negative value, and S is generally spontaneous when it's a positive value. When you look at the equation as it's written, if H is negative and S is positive, there is no temperature that will make G a positive number. So delta G is spontaneous at all temperatures. Now, looking at the opposite, when H is positive, that's generally non-spontaneous. S is generally non-spontaneous when it is negative. There is no value of T that will make delta G negative, so it's never spontaneous. The thought process comes when you're looking at these values. When delta H is positive, which is generally non-spontaneous, and S is positive, generally spontaneous, only at high temperatures will that be spontaneous. I think of it this way. This is a plus, this is a plus, this is a plus. When these two are positive, only at high temperatures. When these are negative, boy, don't we wish that beeping sound would stop. There we go. When both of these are negative, it's spontaneous at low temperatures. Have to figure out what temperature at which something will be spontaneous. Set the delta G value to 0. When delta G equals 0, we're saying that spontaneous, that is the first, that temperature is when it's spontaneous in both directions. Okay. Now, we can also equate delta G to K. K is the equilibrium constant. And remember, the equilibrium constant is the products raised to their stoichiometric coefficients over the reactants concentration. And when we look at this, here is our equilibrium reaction. When delta G is at its lowest, that would be 0. It is at equilibrium, Q equal K. This is equilibrium. When this is happening, the slope of this line is negative, that is spontaneous. When this is happening, the slope of that line is positive, it is non-spontaneous. Okay, here we go. It says A is in equilibrium with B. It has a KEQ that is 2.3 times 10 to the negative 5. What can you conclude about the sign of delta G for this reaction? Well, if KEQ is a small number, that means the reactants are favored over the products. So we can conclude when the reactants are, when K is less than 1, that G is going to be here. The reverse reaction is spontaneous because the reactants are favored. If K is greater than 1, the forward reaction is spontaneous because here is where the equilibrium occurs. And at equilibrium, there are equal amounts of A and B. So we can conclude that delta G in this case is going to be positive because it is the reactants are favored. All right, please read the last portion.